I'm Max Steele. You've seen me in such fine quality educational videos as Chemistry in the Real World, What Now? And there is chemistry in Romeo and Juliet. After all, she did take poison, right? Okay, we're going to be looking today at equilibrium. We're looking at the idea of Q, our quotient, which is a pretty important part. When we look at equilibrium, we look at the idea about the rate that the concentrations of reactants and products, that they arrive at a certain point where products are being made, reactants are being made at an equal pace. It doesn't necessarily mean that our concentrations of our reactants and products are going to be the same. Is it possible? Yeah, but what we're looking at here for K, okay, we have ourselves here an equation, balanced equation, and we have got NaCl that's being broken down into NO and Cl2, and then they go back and they reform. So this is one, again, where this is an equilibrium, okay? I whip my hair back and forth, okay? That's what we need. And then here we have our K, our equilibrium constant is 1.55 times 10 to the minus 5th molar at 35 degrees Celsius. So we have our initial conditions, and here they are. 2 moles of NaCl, 3.3 moles of NO, and 2 moles of Cl2. Now, we dumped all these into a 3-liter flask. Okay, so we dumped these 3 gases into this 3-liter flask, and we're going to take a quick click snapshot. And that's what that quotient Q is about. Now, you'd sit there and say, wait a minute, what do you mean the quotient Q? I understand about K. K is the equilibrium constant. It's the same formula, except instead of K, we use the letter Q because we're looking at that quick snapshot at that moment. What's happening with the reaction at that moment? Is that reaction at that point in equilibrium? And the thing is, Q is going to tell us one of 3 things. There are 3 possibilities. That Q is going to be bigger than K, Q is going to be smaller than K, or Q is the same as K. Okay, and that's going to be depending on its behavior. Okay, whatever that value of Q is, when we compare it to K, we're going to know if the reaction is going to quickly make more reactants, so product breaks down to break more reactants, or is it that we need more product, so more reactants are combined to make more products. Or I whip my hair back and forth, I whip my hair back and forth at equilibrium, at equilibrium. That's the idea behind the Q. Okay, so here we have a problem. We have 2 NaCl gets us 2 NO plus Cl2. Here is our constant K right here. And then we have our moles of NaCl, NO, and Cl2 and a 3-liter flask. Okay, so here we look at molarity. Okay, and the problem that you run into, we cannot work with this. We just absolutely can't because it's not concentration. Remember, a mole is a number. But we do have molarity, which is moles over liters. That would be kind of an important thing. So if we go ahead and we were to take these and divide it by 3, so for NaCl, it's 2 over 3. For NO, it's going to be 3 over 3, and our Cl2, it's going to be 2 over 3. You're going to find that we have a different outcome. We are going to have concentrations, and this is what it's going to look like. So we went ahead to find the concentrations of this. So our 2NoCl gives us a 0.67 concentration, and it's going back and forth for 2NO plus Cl2. And our 2NO is going to be a 1 molar concentration because it's 3 divided by 3. And then here's our Cl2. Let me put the other bracket here. And then we have our other bracket here, which is 0.67. Okay, and this is what we have. This is exactly what we have. And now we have our concentrations, and now we're ready. We're ready to go ahead and do the next thing. Well, wait a minute. What's our formula? The formula for finding our quotient is the same as finding the equilibrium constant. So we're going to say Q is equal to the concentration of our products multiplied by whatever coefficient they have excuse me, divided by the concentration of our reactants. Also multiplied to some constants, to some coefficient z. Now y and z could possibly be the same, maybe, maybe not, okay? But this is what we have. This is our formula for Q, and you'd say, wow, it looks awfully familiar like the equilibrium constant formula. That's because it is the equilibrium constant formula, but we're taking the snapshot. We're substituting Q for K because Q is going to give us that snapshot that's going to tell us which way is the reaction going. Is it at equilibrium? Is it going to shift to the left to make more reactant, or is it going to shift to the right and make more product? See, that's what we're trying to find out with this particular reaction here. So this is what we have, and notice I went for different colors so that you guys can see the different steps. Now we're going to move on, and we know I'm going to go in red, so I know it's going to be products over reactants. Now I also know I have to pay attention to my coefficients here. Notice I have to pay to the coefficient. Pay attention to the coefficient when I'm calculating my Q. Okay, so here we go. Here's our product, okay, and we have our concentration, so it's going to be 1, and that's going to be squared, multiplied by 0.67 over, and in this case here, 0.67 squared. So that's what it would look like, okay? And if we were to go multiply this out, we're going to have 0.67 divided by 0.45. That's what it would look like. Okay? So that's what we would have. Then the next thing we would look at as we divide it out, our Q is going to equal 1.49. Okay? Now they gave us the K at the beginning, where our K is equal to 1.55 times 10 to the minus fifth. Ooh, ooh. So is Q the same value as K? Absolutely not. Is Q smaller than K? No, no, it's not by any stretch of the imagination. But Q is definitely bigger than K. So what does that mean? Well, if Q is bigger than K, guess what? It moves on. That means it's too many products, okay? And you're going to shift to the left. That's what the behavior is going to be. It's going to be too many products, and it's going to shift to the left as a result. This is so not at equilibrium. It absolutely is not at equilibrium. No, no siree. Okay, that takes care of this problem here. Okay, so let's move on. Let's go for another one. What if, guys, what if we went ahead and we flipped our equation? Let's flip the equation. We'll keep the numbers the same. We'll flip the equation, and let's see what would the results be. What would the results be if we went? So again, we have 2NO. Oops. Let me erase that. Let's go back to it. So we have 2NO plus Cl2 gets us 2NoCl. Okay, so this is what we're going to have. All right, and again, we're going to have the same concentrations. So we're going to have 0.67. Here we're going to have a 1, and then here we're going to have, again, a 0.67. This is what we're going to have. So we're going to work through, they gave us that. So now, of course, the question comes down to is, well, hey, what is Q? What is Q? How does it relate to K? Well, remember that Q is going to equal the products, the concentration of the products multiplied to some number N over the concentration of our reactants multiplied some number M. It doesn't matter which letters you use. The idea is the coefficient. That's the important thing. So, our product divided by our reactant. Well, what's our product? Well, we have our product here, okay? And notice we got to go back up here and look at our coefficients, because that's where it's going to come in when you're figuring this stuff out. Okay? So let's look at it. So we're going to have 0.67. We're going to square that because of the 2 there. All right, and we're going to divide that by 1, which happens to be squared. That's difficult. Okay, times 0.67. And this is what we would have. And you're sitting there going, you got to be kidding me. No, no. If you look at it, our Q is going to equal 0.67 molar. That is our Q. And guess what? If we compare Q to K, remember our K, and I'm going to write this in red so that you guys remember, our K is equal to 1.55 times 10 to the minus 5th molar. Now we're assuming the temperature is the same. If we mess around with the temperature, that kind of changes things a little bit. Okay? So that's it. Okay, so here we go. Now we're ready. We compare the Q with the K, and guess what? Q is not the same as K. Q is not, it's nowhere near close to K. It's overshot. It is definitely bigger. Now, not as big as the reaction we did earlier when we flipped it, which is what we did here. We just flipped it to see, hey, what's that? If we take that snapshot, click, click, what is that going to look like? And that's what we have. So what does that mean? That means our reaction, okay, the reaction shifts to the left, okay, to make more reactants. That means we have too many products. Okay? All right, guys, so you got to work a little bit with Q this morning, and hopefully this will help a little bit, make things a little bit easier when we're looking at Q and related to equilibrium. We worked through 2 problems using the same reaction, using the same concentrations, but we flipped the order of the reactions just to see what would happen. Okay? All right, I hope this helped you guys out. You guys take it easy, and I'll catch you the next time.